Hi, welcome to the first in a series of tutorials on the Poisson distribution. Now, what is the Poisson distribution? Well, I've got a definition up here which I'll read out to you, and then we'll run through a few examples at the end. Now, if we have an event that occurs at random in time or space and has a mean number of occurrences lambda in a given interval of time or space, and if x is the random variable, the number of occurrences in the given interval, then x follows a Poisson distribution with mean lambda. Now we write that x follows a Poisson distribution, we write p with a small o, and the Poisson distribution is described by one parameter, and that parameter is the mean lambda. Now, where do you get Poisson distributions? Well, it's all about the number of, the number of occurrences in a given interval of space or time. So it could be, for instance, the number of car accidents on a particular stretch of road in one day. Let's assume that they occur at a mean rate of 1 a day. Well, this could be a Poisson distribution if the events occur at random in time or space. We've certainly got the mean number of accidents. We've got 1, and the interval of space is a measurement of time, that is a day here. And so we could say that the number of car accidents, x, let x be the random variable, number of accidents per day, follows a Poisson distribution with mean 1. Let's try another example. What about this one? The number of bacteria in a milliliter of a particular solution. Suppose they occur at a mean rate of 3 per milliliter. Well, I've got a mean rate, that's 3, in an interval of space. That space is a volume, milliliters. So we could define this as following a Poisson distribution. We could say let x be the random variable, number of bacteria per milliliter, where basically x follows a Poisson distribution with mean 3. And finally, one more example. The number of flaws in a square meter of cloth. They occur at a mean rate of 1.5 per square meter. I gave this example just to show that you don't necessarily have integer values for the mean. We've got 1.5 per square meter. So if we had 2 square meters, that would be, say, 3 flaws per 2 square meters. Well, in this example, we've got an interval of space, that being square meter, and we've got the number of flaws occurring at a mean rate of 1.5, so we can define this as let x be the random variable, number of flaws per square meter, then x would follow a Poisson distribution of 1.5 per square meter. Okay, so there's a few examples. Now, when you've got a Poisson distribution, you're going to be expected to work out probabilities of a certain number of events occurring. Now, there's a formula for this, and it's this one here. Now, I'm not going to prove to you that this is the formula for a Poisson distribution. It's beyond the scope of these tutorials. All I'm just expecting to show you in this tutorial is how we use it. I'll explain what it is. We've got if x follows a Poisson distribution with mean lambda, then the probability that there are r successes is given by this formula, e to the power minus lambda multiplied by lambda to the power r over r factorial. Now, I hope you're familiar with e, the constant e. You'll find it on most calculators. Its value is 2.718 and so on. And hopefully you're familiar with r factorial. That's R with an exclamation mark here. Some of you might call it shriek, R shriek. Okay, but I'm going to say R factorial here. And you'll find this function on any calculators. For instance, if you had 3 factorial, it's short for 3 times 2 times 1. That would be 6. 2 factorial, 2 times 1, that would be 2. And if you have 0 factorial is defined as 1. And what I want to do now is just show you one example on using the Poisson distribution. Now suppose we had a typist. This typist makes errors at a random rate of 2 per page. And we've got to find the probability that the typist makes no errors and more than 3 errors on a page. So if I assume that this is a Poisson distribution, then I need to define my random variable x. And so the random variable x will be the number of errors per page, where x follows a Poisson distribution with mean 2. Now then, if I'm to work out part A, that would be the probability that the number of errors is 0, no errors. Alright, now to do that, according to the formula, it's going to be e to the power minus lambda. Lambda is the mean, 2, so it's e to the power minus 2. Then lambda to the power r, so that's 2 to the power r, r being no successes here, so that's 0, divided by r factorial. R, remember, is 0, so that is 0 factorial. Now, if you work this out on your calculator, 2 to the power 0 is 1, 0 factorial is 1, so really all you need to type in is e to the power minus 2. And if you do that, you should find you get 0.13533 and so on. And if I round that up to, say, 3 decimal places, we've got 0.135 to 3 decimal places. So, not particularly difficult. Let's try part B now. More than 3 errors on a page. Now this is going to be a little longer because the probability of making more than 3 errors on a page, you could get 4 errors, so that'd be x equals 4. You could make 5 errors, x equals 5, and so on. In fact, the number of errors per page is undefined. Okay, you could make 6, 7, 8, 9, who knows? There's no limit, no end to this, unlike, say, in the binomial distribution where there are a finite number of trials. So how am I going to get around this? Well, what we can do is, knowing that x can be no errors, 1 error, 2, 3, 4, 5 and so on, knowing that all the probabilities would add up to 1, we can say that this is the same as 1 minus the probability that x is less than or equal to 3. Now that we've got that, I just need to work this out as being the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 and finally plus the probability that x equals 3. Now I can use the formula, and the probability that x equals 0 is going to be the same as we had up here. That's e to the minus 2 times 2 to the power 0 over 0 factorial. For the probability that x equals 1, it's going to be e to the minus 2, 2 to the power 1 over 1 factorial. And similarly for the others, x equals 2, e to the minus 2, 2 to the power 2 over 2 factorial. And for probability x equals 3, e to the minus 2, 2 to the power 3 over 3 factorial. Now I could get on the calculator now and just work this out, or what I like to do actually in calculations like this is just to pull out e to the minus 2. Saves me having to type it into the calculator all the time. So what I would have is e to the minus 2 is a common factor, and I've then got 2 to the power 0, which we know is 1, over 0 factorial, which is 1. So I've got really just 1 there. For this term here, I've got 2 to the power 1, which is 2, over 1 factorial, which is 1, so I've got 2. And you can find that you can do quite a lot of this just in your head, rather than waste time on the calculator. This one here, 2 squared is 4, divided by 2 factorial, well that's 2, and 4 divided by 2 is 2, so put that in. And for this one, we've got 2 cubed, which is 8, and 3 factorial is 6, so you've got 8 over 6. So 8 over 6. I could have cancelled that down, I know, to 4/3, but it's quite quick to just do that sum. Well, if you do that anyway on your calculator, whatever, you should find that you get 1 minus 0.85712 and so on. So do check that. And then if you subtract that from 1, you'll find that you get 0.14287 and so on. And if we round that up, I'll just put it over here, you'll find you'll get 0.143, say, to 3 decimal places. Alright, well that brings us to the end of this tutorial. I've limited it just to the one question here, but in my next tutorials I'm going to expand on this. We're going to look at further questions where I change the mean over different intervals, and I would definitely suggest you have a look at that.